I published this circuit a few days ago, and in this video I've used another transformer. That transformer is here. The primary is 2 ohms, the secondary 65 ohms. It was, as far as I know, a transformer that was made for 230 volts going to 12 volts, and now it is reversed. I had questions in the early video about the duty cycle, and perhaps I can show here how that worked anyway. This transformer is suitable, but it doesn't have a very good efficiency. When we consider the primary frequency that is sent in, primary current, primary voltage on different frequencies between, say, 50 Hertz and say 500 Hertz, and then at the output voltage. And here you can see, for instance, that this transformer doesn't produce so much light, and it works now on 39 Hertz, and it works on 2 volts, and the current that the circuit draws is 1 ampere. So 2 watt in approximately, and this is the amount of light that is generated by the noble gas lamp. That's not much. Oh. So let's see what happens when we change the bias. I change the bias now. 500k potentiometer, and here it stops. And you can also hear that the frequency is no longer present in the transformer. Say 40 Hertz, not present. So let's see when we go to higher frequencies. 39 Hertz. Now you can hear the transformer. You can see the neon light that gives an indication about what happens. So for instance here on 175 Hertz I have to do something with the bias potentiometer here to see whether we can get some energy out. No, that doesn't work on 2 volts. So let's take a higher voltage, and you see that the tube suddenly lights up on a higher voltage. Here we have 5 volts on 4 ampere. That's of course completely unreal. Far too much energy that has to be driven into the primary of the transformer. So we go back now to, say, 1 ampere, 2 ampere. At say 4 volts, frequency 175 Hertz, and the lamp lights up, takes up approximately 8 watt here in this part of the circuit. Let's see whether the bias can do something good. No, not at all. Let's see whether the frequency can do something good. I will change the frequency now 300 Hertz, and this is the waveform. You see, there is a difference between the time during which the Darlington is driven, and it gives a kind of good result. 5 volts, 1.5 ampere, say 6 watt in here, and say this little amount of light out. So let's see what the duty cycle can do. Difference in the duty cycle. Now it is already difference in the duty cycle on 300 Hertz, but anyway, I take another duty cycle. So here is in a kind of way the optimum on 300 Hertz. I now go to a higher frequency. It stops. That has all to do with the properties of the transformer. That performs best, its best on low frequencies. And then I mean between say 50 Hertz and 200 Hertz. So we go back now to a lower frequency. And normally the tube will start, but this frequency is still too high. So here we have more or less the optimum frequency. And now I differ the duty cycle somewhat. The current will change. Lower frequency, higher frequency. The supply voltage changes, of course, due to the load that the Darlington sees. Higher current means a lower voltage. It's not stabilized here. So these are all the effects that you can encounter when you do experiments with these kinds of noble gas lamps. And very funny to see, you also see here the resonances. When I change the frequency, you can see that the resonances, the darker and the light bands in that tube move. That's very, very strange, interesting to see. Funny also. And for first experiments, always a good idea, use a classic neon tube. That neon tube will always show whether there is a high voltage on the secondary or not. So, this is the not better choice in this application, but it could be that when you connect here an incandescent lamp with a certain high ohms resistance, that lamp will light up due to the quite high current that can flow in this case. Because we use here a transformer with a ratio between 2 ohms and 65 ohms. So that means that the current at the secondary can grow to quite high value. Of course you have to test that, and I will test it, and when I know more, perhaps I will show the results. Anyway, the Darlington doesn't get hot. This gets hand warm. this driver transistor doesn't get warm on 750 Hertz, and this waveform. And you can also see that when you change the level, the input level to the Darlington, that has an effect. It has an effect on the amount of light, on the current that the circuit takes, on the voltage. So it's quite an advantage and a serious, interesting experiment to find out the transformer to which your noble gas lamp performs at its best, given a certain voltage and a certain current. So maximum light out at minimum voltage and current on the primary of that transformer. Let's change the bias somewhat. Interesting on this frequency. Well, it stops suddenly. That's more or less common. And also interesting to see, I switched the supply voltage off, and often you can see that the lamp lights up more. And that's an indication that you have to adapt your supply voltage. Let's do that again. Of course, all experimental. And these are all very, very interesting experiments to learn a lot about electronics, and of course it's all pure fun.